In virtual worlds representing large-scale outdoor environments, clouds are an essential piece of realistic atmosphere. They're not just a part of decoration, but a powerful artistic tool, enabling you to define weather conditions and emphasize the scale of your virtual world. UNIGINE Volumetric Multilayer Cloud System meets the strict requirements of quality and performance applicable to enterprise flight simulators, where clouds are a key part of simulation. Volumetric clouds are rendered using ray marching based on coverage data and refined with a set of sophisticated noise distortions, providing artists with full control and extreme level of detail. All 10 main types of clouds presented in nature are available in UNIGINE out of the box as configurable presets. To start using volumetric clouds in your UNIGINE project, make sure that rendering of clouds is enabled in your scene. Right-click with the Shift key in the viewport to open the Creation menu, then choose Sky, Cloud Layer, and select the desired preset. Let's start by adding altocumulus clouds. Place the new node on the ground, transform it if needed. The cloud layer is added as a child of a dummy node, ensuring it is placed at a proper altitude, typical for this type of clouds. You can add as many layers as you need and quickly make the scene's atmosphere look natural. Storm clouds, Cumulonimbus, can have an arbitrary shape. 3 variants are available out of the box, so you can create a storm front in a snap. The cloud's visibility distance is limited by the camera's far-clipping plane. Increase the value to see the clouds up to 400 kilometers away, which is enough for both average and advanced simulation projects. The cloud system is completed by rendering of environment and the world light source, providing realistic shadows and lighting. Aerial perspective is achieved by means of environment scattering simulation. The type of clouds in a cloud layer, their visual representation and behavior are defined by the material assigned to the layer. By default, it is read-only. You can customize any cloud preset by creating a child material from it. Let's dive into global settings for clouds first. Open the corresponding section of the Settings window. Quality and performance requirements of user projects may vary, so the cloud settings should be adjusted properly. There are several groups here. Let's have a quick look at them. In the common settings, enable the ground shadows to cast shadows on the ground. Shadow casting is toggled per cloud layer in the material settings and is usually enabled for new layers. We are going to consider this feature in more detail later. By default, cloud layers are sorted roughly based on their height. In case you have intersecting cloud volumes, toggle Accurate Layers Sorting to get a much more realistic interaction between layers. When enabling this feature, be aware that ray marching quality may reduce as samples shall be distributed among all layers. Presence of clouds and transparent objects in the same scene may reduce performance. For this task, UNIGINE offers simple optimization, the Transparent Order mode. You can choose to render clouds after transparent objects for cases when the camera is mostly placed above the clouds and may observe some transparent objects on the ground, windows, particle effects like this forest fire, and so on. The same mode can be used when the observer remains on the ground and transparent effects can appear only above the volumetric clouds. For example, a sky object with sprite clouds on it. However, this is a very special use case. Choose Render Before Transparent, and clouds will be moved in the rendering sequence before all transparent geometry except water. Use this mode when transparent geometry can only appear between the camera and clouds. In more complex scenarios, when the order of rendering of clouds and transparent objects can change at runtime, for example, the camera has arbitrary position and movement. Use the Sort Transparent mode to avoid artifacts. This enables rough bounds-based sorting for all transparent objects relative to clouds and the camera and adjusts rendering order. The Detail Distortion setting determines the type of texture used for clouds distortion. It is applicable in certain cases. We'll consider this a bit later. The distance of soft transition for objects penetrating the cloud volume is defined by the soft intersection value. The next section is the quality settings. For your convenience, there are several presets intended to streamline quality configuration from low to ultra quality, including optimized presets with interleaved rendering enabled. Choose Custom to access ray marching settings for fine-tuning. Adjusting this section requires complete understanding of all parameters, so be careful when using the custom option, as the look of clouds and performance in your scene may degrade a lot. Rendering of volumetric clouds implies tracing rays from the camera for each pixel. The visual quality primarily depends on several base parameters that define the number of iterations and precision of calculations at certain rendering stages. Sampling quality enables you to choose the precision of clouds transparency calculation. Lower levels result in less accurate shape and density of clouds. The effect is mostly noticeable along the edges of clouds. By selecting the highest sampling quality, you can observe wider semi-transparent areas. However, visual difference between lower and higher levels is not significant, and it is recommended to use the least possible level for higher runtime performance. Lighting quality and the lighting section relate to ray-traced lighting calculation for all cloud layers. UNIGINE adopts the cone-sampled lighting technique. Lighting in a cloud region is computed by measuring transmittance at several sample points that form a conic shape to include neighboring regions, as the light at any point in a cloud is greatly affected by the light in regions around it. Lighting quality defines the number of samples used to calculate lighting in every pixel. It also has a significant impact on performance and should be adjusted carefully. Use the lighting trace length parameter to define the maximum length of each ray in meters. Too short rays might not reach the top of the cloud, resulting in inaccurate depiction of shaded regions, while too high trace length makes thinner clouds look brighter and less dense. You may increase the value to make the Cumulonimbus clouds look more realistic, as they are usually huge and very dense. Lighting cone radius defines dispersion of samples in a cone, making shaded regions smoother. With lower values, shadows are prone to be sharper, as each light ray is going along a straight line, which may result in unnatural behavior when the position of the sun changes. The last parameter is accountable for the distribution of lighting samples along the trace length. Higher values make lighting samples start closer to the beginning of the trace range and diversify sampled lighting. Samples count defines per pixel quality of rendered clouds. Note the impact of this parameter on the result. Lower values result in loss of details and an extreme level of noise. Distant clouds may become invisible due to absence of subpixel sampling. The higher the value, the more samples define the final color of a pixel, resulting in a better and more smoother look of clouds and a higher load on the GPU. By increasing the accuracy of ray marching steps, you can get rid of extra noise and provide more accurate cloud density, which again takes a bit of performance. Downsampling and interleaved rendering are used for optimization. The downsampling rendering parameter determines the resolution of the cloud screen buffer relative to the current screen resolution. Select lower values to quickly make rendering faster, or choose full for pixel-perfect quality. When clouds are viewed at a significant distance, no matter from below or above, and the observer's velocity is small enough, enabling interleaved rendering can provide a significant performance boost. This technique enables skipping every 2 to 8 pixels when rendering clouds. The options 4x4 and 8x8 are much more aggressive, but still appropriate for projects with relatively calm motion of the camera. Note the reconstruction artifacts. When the camera rotates quickly, however, the look of clouds is good enough if the camera represents a person walking on the ground. Although downsampling and interleaved rendering greatly improve performance, they might decrease visual quality a lot. Note that aggressive interleaved rendering is not appropriate for inside the cloud cases. The picture suffers from heavy smearing and noise. For that, a couple of fixes are available. If you have the half downsampling or the 2x2 interleaved rendering, engage the depth-based reconstruction for fast upsampling and depth-dependent reprojection, which also fixes obscuration of geometry inside the cloud. Use the threshold parameter to define the depth difference starting from which the pixels are considered to be unrelated to clouds. Use interleaved rendering temporal option, available also for the 2x2 interleaved rendering mode, to engage additional temporal accumulation of noises and get rid of heavy jittering. Insufficient number of samples often lead to banding artifacts. To prevent this, clouds are sampled using jitter with temporal accumulation of results. You can control the amount of jitter for lighting calculation and for clouds rendering in areas within and between the clouds, as well as the number of noise iterations for fine-tuning. In the real world, cloud layers are not flat. They rather follow the planet's curvature. Enable the rounded feature to toggle visual curving for clouds on. This option is used to make clouds fall over the horizon and look more natural, imitating the planet's curvature. You will need to specify the planet radius. If there is no need in strict simulation, do not stick the actual dimensions of the planet you simulate. This value is to be adjusted visually. The dynamic coverage settings define the quality of dynamic coverage alteration. The coverage data can be altered locally for a cloud layer by using a field weather node. This is applicable for cases when it's needed to create controlled local storms or clouds with changing coverage. Specify the bounds of the area, a new coverage texture, attenuation, and other parameters, and the field weather will replace clouds within its horizontal bounds. The number of such objects is not limited as their impact on performance is insignificant. You can transform each field weather separately and control the change of the atmosphere on the fly. Dynamic coverage settings define the resolution and the spatial size of the dedicated buffer into which additional coverage textures are rendered. If you need to see the effect at a distance, increase the dynamic coverage area value, defining the distance from the camera where the effect is visible. But beware of quality degradation that comes with higher values as the dynamic coverage buffer is mapped onto this area. It's also possible to preserve more texture details by choosing a higher resolution of the buffer at a cost of performance. The key point here is to find a trade-off between the best visual quality and performance while keeping resolution and size of the dynamic coverage area as low as possible. Field weather objects are useful for local coverage replacement and creation of insets in a cloud layer. However, settings of a separate cloud layer provide more room for control and better quality. That's all for global cloud settings. Let's proceed to customization of clouds. All built-in cloud presets are implemented as children materials of the cloud's base, the base material for clouds, with a rich set of settings enabling artists to control cloud formation, look, and behavior. To start configuring your cloud layer from scratch, create a new child material. There are two types of cloud layers. Infinite, a global cloud layer spread infinitely, and defined. This type of cloud layer is limited to a certain area and is used for regional weather. Defined layers have the layer size parameter accountable for its horizontal dimensions and the cloud's region mask, where a single channel texture defines the region of clouds within the given bounds. By default, it has a shape of an irregular circle. By combining several defined cloud layers, you can simulate different cloudiness and weather in different regions. For example, to create an upcoming storm or implement a global weather system. One of the main parameters defining the look of the cloud layer is its height specified in meters. All natural cloud types have their own typical heights. The shape of clouds can be defined either by a coverage texture or by a 3D texture. The coverage texture option is suitable for most of the natural cloud types. Coverage textures for all built-in presets are provided as core SDK assets and cover the most cases. But if you intend to customize clouds, you should know that clouds coverage texture should have 3 channels, where red channel stores a coverage map and determines cloud density in a horizontal plane and shape of shadows cast by the layer. There is no need to apply noise when authoring a custom texture to add more details. It should describe the base large-scale distribution clouds. Green channel defines a storm cloud map. Storm clouds appear denser and less distorted. Blue channel stores a height map where the white pixels correspond to the layer height and black pixels correspond to the minimum possible thickness for the current settings. The coverage texture is tiled horizontally, providing the cloud layer with data for cloud formation in every spatial point. You can control the size of tiles by adjusting the coverage size available in the geometry parameters. In large-scale worlds, when observing clouds at significant distances, tiling becomes noticeable. One of the solutions here is to engage the use of the alpha channel of coverage texture for additional masking, applied according to the alpha size parameter. The second out-of-the-box solution is to enable fixed coverage tiling that eliminates coverage tiling procedurally. Use this feature only when you really need it, as it may affect performance. Geometry parameters define the basic shape of the clouds. You can control the contrast of the coverage texture. Higher values increase the difference between dark and light pixels, resulting in sharper edges and less amount of generated clouds. You can use it to gradually change cloudiness at runtime. Note that completely white and black pixels of the coverage map will not be affected by this adjustment. Switch to the curve contrast type to get more control over the contrast based on the layer height. For example, to make more irregularities in the middle. The same way you can adjust cloud density to simulate thinner clouds like cirrus. Note the performance hit on lower density values as it gets harder to render lots of transparent regions at once, so it is recommended to provide a ready-to-use coverage texture and make little adjustments to density. Fine-tune height values by adjusting the coverage height remap parameter. The values from the coverage texture are spread up along the layer height. Bottom fade controls dissipation of bottom regions, while storm cloud factor enables you to amplify the values of the storm cloud map by the coverage texture to simulate rainy weather. Noise parameters are applicable only for layers using a coverage texture and define actual clouds formation. Clouds are generated based on 4 3D noise textures of different complexity, combined and applied to regions at different heights, thus simulating accumulation of heavy particles at the bottom. You can scale the noise to achieve the desired look, but extreme values make tiling noticeable at large distances. In this case, when there is no other way to avoid artifacts, use noise tiling reduction. Noise threshold defines the range of noise values for cloud generation. Higher values result in less regions filled with fog and a rougher cloud experience. This can be tweaked by the noise threshold extent parameter. Increase the value to extend the upper noise limit, smoothing out cloud formation. Take note that shadows from the cloud layer, if they're enabled, are not affected by these parameters and may need some adjustment if the configuration has changed significantly. Noise textures are sampled with regard to MIP levels based on the distance from the camera. If you notice serious degradation of noise quality with the distance, increase the noise MIP offset parameter to shift the MIP levels used, sacrificing some performance. The curves of the noise falloff define the height range of influence for each of the 3D noises. Red channel corresponds to the coarse noise level, while alpha corresponds to the finest noise. These values are to be tweaked only if additional precise adjustment is needed. By switching to the curve mode for these parameters and the ones from the geometry settings, you can get fine control of the layer shape and achieve a complex custom look of clouds. Another cloud shape type is 3D texture intended to simulate clouds of a complex arbitrary shape, like Cumulonimbus clouds. It uses a three-dimensional single-channel texture whose values form a volumetric shape. When creating a custom 3D texture, bake density values of your slice geometry to a 3D texture. This can be a DDS volume texture or a normal image with slices stacked vertically. When importing such a texture, select the 3D texture type, then specify the texture in the material settings. You'll need to prepare a separate single-channel texture to define a custom shape for the shadows cast by the cloud layer. The 3D texture threshold parameter enables you to cut out unwanted regions of the cloud shape. Use the extent parameter to make edges smoother. You can also control these two values along the layer height by selecting the curve threshold type for more precise tuning. Other geometry parameters are the same. Now, let's go to extra noise. While the noise is used to form clouds, the extra noise serves for cutting out regions of clouds to add more shape variations. Use it when the base form and details are insufficient. For example, when the shape of the layer is defined by a 3D texture. All the parameters are similar to the noise settings, except that higher noise values here cut out more regions and make clouds less dense. Use extra noise for coverage texture-based layers to get more control over the look of clouds. Detail settings enable you to control additional refinement of the cloud shape. You can specify the detail cutout intensity and noise size, and the same values for turbulent distortion. Let's apply extreme distortion to make the effect more prominent. Here, the detail distortion setting plays an important role. With a 2D texture, you can see an excessive vertical extrusion. Switch to the 3D texture option to get homogeneous details and better quality, paying with another bit of performance. The last parameter here controls the inversion of detail noise and enables switching between more wispy clouds at the 0 and more billowy clouds in the middle. At the value of 1, detail distortion is applied to the areas unaffected by it by default. The distortion section stands for curl noise distortion applied to the layer. Adjust the intensity and size to get a turbulent look of clouds. It's also possible to apply skew distortion in the direction of the wind to a portion of the clouds. Control the height of the layer starting from which clouds are to be affected by the skew distortion via the corresponding parameter. 0.5 means the middle layer. Shading of clouds works together with environment scattering simulation in the current world light source. Ambient lighting for clouds is calculated based on the dynamic environment cube map, so changing the time of day and the environment texture immediately affects the shading of clouds. The dedicated section of parameters controls the influence of each factor separately and enables fine-tuning. Default values are okay for most cases. The self-shadows flag toggles self-shadowing of the cloud layer and accurate density-based lighting calculation. You can control the color of lighting from the sun depending on how deep light rays penetrate the cloud. For example, you can make photons lose certain components as they go through the cloud. The anisotropy by density curve maps higher cloud density values to lower intensity of light scattering inside the cloud. For example, in this default configuration, light is scattered in various directions in more dense regions of the cloud, making the direct sunlight dimmer and its reflection more apparent when looking away from the sun. Ambient color by density, a color multiplier for ambient lighting, can be applied for regions of clouds of different density. Another color multiplier for ambient lighting, ambient occlusion by coverage, depends on the brightness of the coverage texture. Intensity of each color component depending on the layer height is controlled by the next ambient occlusion by coverage falloff curve, which is usually used to avoid darkening of ambient lighting at the top of clouds. You can control intensity, attenuation, and saturation of sunlight passing through clouds. There are settings for saturation and intensity of ambient lighting at the top and the bottom of the cloud as well. Multi-scattering intensity controls approximation of sunlight scattering. This is a view-dependent effect, most noticeable when looking at the clouds from the side relative to the sun direction. Attenuation coefficient is another parameter for fine-tuning of transparency attenuation, enabling you to quickly make edges of clouds look smoother or sharper. The haze gradient parameter makes sense only if the haze gradient mode is not set to physically based. It enables you to fine-tune the degree of gradual fading of clouds into the haze with the distance. The next section controls shadows cast by the cloud layer. You can toggle shadows via the corresponding flag. Check Receive Shadows to enable shadows from upper layers. A set of parameters gives you an ability to fine-tune the look of shadows from this layer in case they do not accurately represent the configured cloudiness. You can control intensity, contrast, multiplier, and subtraction of shadows. Wind settings control the temporal change of clouds at runtime. Wind speed along X and Y axis shift the coverage texture horizontally. The speed along the Z axis defines the speed of vertical noise shift. And the last parameter, wind deformation, controls the intensity of deformation of clouds as they move. That's all for clouds customization and settings. You can find more details on the volumetric cloud system in our online documentation and check out the built-in art samples illustrating cloud features and customization in UNIGINE.